All right. Josiah, when we take notes, you just get to copy what's up there. Okay. So our objective today is to study trapezoids and information about trapezoids. So to learn and understand, trapezoids. This comes from lesson 5.5. All right, so a trapezoid. First, we need to know the definition. And Josiah, just to let you know, we have two sets of cards that we keep, and we keep them separated. One is our vocab cards. You'll know it's a vocab card because I'll just underline it. The other set of cards are the theorem, postulate, property cards, and I'll underline them and put a star next to them. So you're going to just make a set of cards of each, like flashcards, and then you get to use the theorem cards on tests and quizzes until we get to a point where I tell you you can't. And you never get to use the vocab cards on the quizzes and tests. And you will turn both sets of cards in on test days only, and I'll grade those. And you get a point per having each one, okay? And I still don't have my paper for you because my computer is dead at home. What has it on it, so I'm looking to see if I have it someplace saved on this one. So a trapezoid is a quadrilateral, because we are four-sided figures still. And here comes the important part. With exactly one pair of parallel sides. Every other quadrilateral that we've talked about had both sets of opposite sides were parallel, because all of the ones we talked about could be proved that they were parallelograms. Okay, so this is what makes a trapezoid unique, is that it has one and only one set of parallel sides. That's another way of saying exactly, is one and only one. Okay. So the parallel sides are called bases. So we're going to call the bases of a trapezoid. These are the parallel sides. Of a trapezoid. Now, the reason why I added of trapezoid as part of the bases is the fact that if you just wrote bases, we've talked about bases a lot of different ways, so we're specifically referring to the base of a trapezoid. And then the legs of the trapezoids are the non-parallel sides of a trapezoid. And just to give you a picture, generally the two parallel sides are horizontal, though you will on occasion see a parallel or a trapezoid drawn this way. Where the parallel sides are the vertical ones. So those parallel sides are called a base. And the other two sides that aren't parallel are called leg. You can have all sorts of different types of trapezoids. In fact, if you look at this one, we'll add a little symbol for you. We would call him a right trapezoid. Okay. And those are all fine and dandy, but the issue becomes there's not a whole lot that we could get from that other than, oh, if we have parallel sides, then same side interior angles are going to add up, are going to be supplementary. If we drew, we might be able to get, yeah, that'd be about it. So we could deal with the angles, would end up being supplementary both here and here, because here's your parallel lines, here's your transversals, these are same side interior angles. So here, these two would be supplementary, these two would be supplementary. But again, when we have theorems and proofs, we're usually dealing with a figure that has more, what's a good word to use? It's more regular. And so the next type of trapezoid is the one that our most of our, no, not most of them, but some of them are based on, is an isosceles trapezoid. So everybody done with this screen? May I move? Yeah? So let's have one more definition of an isosceles trapezoid. And what's going to make an isosceles trapezoid unique compared to the other trapezoids? It has nothing to do with the bases, it has everything to do with the legs. And so if we have legs that are congruent, then the trapezoid is called an isosceles trapezoid. So it's a trapezoid with congruent legs. So in addition to our parallel bases, we now have legs that are congruent. Okay? So I've got two theorems. Well, I've got a theorem, definition, a theorem. And then that would pretty much wrap up today's notes. So the first theorem deals with this idea of an isosceles trapezoid. Okay, let's see if you guys can think what would be true. Now this theorem doesn't have a name. Sorry, you're going to have to write it out. But blissfully, it's fairly short. So if I have an isosceles trapezoid, what are some things you think you could conclude about parts of that trapezoid? Dakota, I saw your hand first.
Opposite angles are congruent. Opposite angles on the bases are congruent.
Opposite angles.
Base
Okay. So this one and which one?
The one on the right now. Opposite.
Like this?
Yeah.
Okay. So you're saying these base angles would be congruent with these?
Yeah.
Yeah, if you think about it, if these two are supplementary and these two are congruent, we have a theorem that says if two angles are supplements of congruent angles, then those angles are congruent as well. So that's precisely what Theorem 515 deals with, is the idea of base angles being congruent. So, and remember, it's very specific. Base angles of isosceles trapezoids are congruent. So he'll come back. Come, my friend. Magic. So basically what it's saying is those angles are going to be congruent to each other. And because of what we just talked about, we can also know that those angles would be congruent to each other, because we end up having two bases, so it kind of makes sense that we would have two sets of base angles. Okay. Now, what I'm going to do is have you guys kind of look at the, we could talk about how you would prove this. So if you were doing a proof on this, you would be given that you have a trapezoid, and we'll use ABXY. And because we want it to start with it being isosceles trapezoid, we have to either say it's an isosceles trap or be specific what are the two congruent sides. So the way that the book wrote it is they did write it with the two congruent sides. So segment BX congruent to segment AY. So again, here's a little picture. Let's do him down a little lower. Bless you, bless you. So from the given, we're told these two sides are congruent. So we know it's a trapezoid. We have two legs that are congruent. Therefore, it is an isosceles trapezoid. Okay. So you could say this is an isosceles trapezoid by the definition of isosceles trapezoid. Right? Now, what do we want to prove? Oops, that was supposed to change color. We would be proving that angle, and because I only have single angles coming out, I can use single letters. So I want to prove that angle X is congruent to angle Y, but I could also be proving that angle B is congruent to angle A. So unfortunately, there's nothing from a trapezoid that I could use on any theorem or postulate we've talked about in the past. So what I could do is add some auxiliary lines so it mirrors the shape that we've been studying. So what are some shapes that we could use that would help us out? A couple ideas. Isabel?
Triangle.
We could somehow manage to get some triangles involved in there. What else, Sarah?
Triangle and a parallelogram.
So somehow parallelograms or something that's a parallelogram, maybe a rectangle, a square, whatever it is, okay? And so they do have two ways to solve it. So I'm just going to give you some brief ideas of what they showed. So if this is your AB, X, Y, and we know that this is congruent to this, they said, okay, what I want you to do is create a parallelogram. In creating the parallelogram, you're actually going to cut off a triangle. Okay, so you're going to do this. You're going to draw a line so that it's parallel to segment AY. Okay, and we have a postulate that says there is, through a point outside a line, there is exactly one line parallel to the given line. Okay, and we could use that. So this guy would be parallel to this guy. Okay. Now, in addition, we would want to add a couple of angle numbers. Here's angle 1, here's angle 2, here's angle 3. And so what we want to get is angle 1 congruent to angle 3.
We had a problem just exactly like this. I think the last night I told you.
Remember how many times I tell you that? That the night before we learn a theorem, they tend to give us a practice problem, and all of a sudden it kind of reveals itself, and then wham, we get the theorem, and we go on from there. So if we have a parallelogram, we would get angle 2 and angle 3 congruent to each other, right? Because we have parallel lines cut by a transversal. Corresponding angles would be congruent. Okay? All right. What else could we do?
Since bx is congruent to ay, then you can, through, I think it was definition of parallelogram, ay is congruent to, never mind. I did not know what I thought.
Okay. Well, you're on the right track, actually. Isabel?
Because opposite sides of the parallelogram are congruent, the AY is congruent to Z.
Oh, yeah. We'll put a letter there. I'm so sorry. We'll call him Z. Yeah, we have to put that in there. Right. No, you're on the right track, Rachel. She's exactly right.
You can substitute in using transitive property that AY is congruent to ZX.
Yeah. This would be super simple. We know from the given we have a trapezoid. So we know that we have two legs that are congruent. They can't be the bases. Andy, wake up. So we've got AB and XY are going to be parallel to each other. Well, then we add in that BZ so that it's parallel to AY, and now I've formed a parallelogram, ABZY, and both sets of opposite sides are parallel and congruent. So that means AY and BZ would be congruent, But AY is the same as BX. So exactly, through transitive, I can get BX congruent to BZ, which creates what kind of triangle? An isosceles triangle. And if I have two sides of a triangle that are congruent, then the angles opposite those sides are congruent. So we get angle 1 congruent to angle 2. So I had 1 congruent to 2, 2 congruent to 3, transitive property congruent says 1's congruent to 3. So once we get that, we've proved it. So that would be one way to solve this. Dakota?
Why would you use transitive?
Because
you don't have a substitution.
there is no substitution property of congruence. That's number one. Okay. Number two, this is really how, if you think about it, the whole transitive property was designed for. If you have an overlap, okay, that gets you down to angle 1 congruent to angle 3. Okay.
I'm still confused on how you get the BZ congruent to the BX.
Well, we started with, for this one, we would get that ABZY is a parallelogram. Because we've created it to be that. And then we know from parallelograms that opposite sides of a parallelogram are congruent. But we were given that BX is congruent to AY. So this was given to us. So then through transitive, that's not BY, that's a BX. You get that. And then you have that isosceles triangle, and that's where we got angle 1 and angle 2, and so on from there. Okay, that was one way. And then they also, you can look in the book, they also did it by dropping altitudes from B down to XY and from A down to XY. So it would look something like this. And then they would create, get those two triangles congruent, and we would have parallel lines. We would actually, with the parallel, from here, this would have to be done. We would have one set of parallel lines. We would end up having right angles everywhere. Therefore, we'd have a rectangle, okay? And then we can take all the information we know about rectangles, and we'd get these two sides being congruent to each other. So then we would have a hypotenuse and a leg for each of those triangles. So then we could get angle X congruent to angle Y through CPCDC. So that's an other avenue to do as well, okay? All right, so that's the first one. Now I got one more word, vocab. We've had a lot of vocab today. And we've seen this word before, but now we need to apply it to a trapezoid. So the median of a trapezoid. Median. So the median of a trapezoid is the segment that joins the midpoints of the legs. Okay, so we'll draw a picture of that. So we've got our trapezoid. And then we're going to give you midpoints. We'll connect them together. Let's get some letters in here. We'll call this R, S, P, Q, R, S, M, and N. So we've got M is the midpoint of segment SP. N is the midpoint of segment RQ. we can add, therefore, those ideas. And this is starting to look a little bit like something we talked about, I think it was in last chapter. Maybe it was earlier in this chapter.
Oh, yeah. If there's like three, yeah.
It was in the beginning of this chapter.
I remember that.
Okay. We've got...
Three parallel lines that cut by two transversals, then they're like congruent.
they cut off, well... It's more like 511 says the segment that joins the midpoints of two sides of a triangle is parallel to the third side and half as long as the third side. It's kind of that same notion, other than we don't have a triangle peak. But what the theorem that we get for this reveals, oops, sorry, back to black. Theorem 519 states the median of a trapezoid, and notice that the trapezoid didn't need to be isosceles. One is parallel to the bases. Two has a length equal to, and here comes the question. In the triangle that came up to a point, the median was half the length of the third side, or the other side. We've got two bases, though, here. So what do you think we're going to do to figure out the length of the median, since there's two bases to be considered? Sarah's cheating and looking in the book. I have two lengths, and I'm thinking about the median. And median is another way of finding average. So this is just, we're going to deal with average here. So the median of the trapezoid has a length equal to the average of the bases. Okay. Do you guys remember the formula for the area of a trapezoid?
It's base times height divided by 2.
No, that's a triangle.
Oh, yeah.
Oh, you can
base.
you can use it like to multiply two triangles.
Yeah, we're doing that.
Okay. It is kind of like having two triangles.
Yeah.
Okay. If you think about it,
Yeah.
1 times b divided.
okay, you could create two triangles and figure out their areas and add it together. Okay. However, they are just talking about they share this piece. Okay. So this goes back to that theorem 511 that this piece here is going to be half of this piece. This piece here is going to be half of this piece. So if you're figuring out the area of each of those triangles, so you're going to have 1/2 base times height, 1/2 times base times height. If the area of a trapezoid uses the same notion as what we have here. It's 1/2. We're going to have to multiply it by the height, which is going to be, some value that goes from the top to the bottom. But it's going to be times the sum of the bases. If I pair up half with this, I'm finding the average of the bases, and I'm multiplying it by the height. Okay, so there's a direct relationship between this notion, the second part to this theorem, the median of the trapezoid has a length equal to the average of the bases. When I'm figuring out the area of a trapezoid, I'm using that median to be my base number and multiply it by the height. So that's where, again, that idea comes from.